So sum and product of the roots starts from this basic idea that if we know the two roots of the general quadratic are alpha and beta, then it must be possible to factorise our quadratic to be a outside of x minus alpha, x minus beta. And if I expand the right hand side out and group, make them monic, so divide both sides by a, because they are identical, we know the coefficients must be equal. So therefore, the sum of the roots, alpha plus beta, must equal minus b on a, and the product must be always c on a. Okay, so that's where those two little formulas come from. So if we want to now create a quadratic equation, if I want to form a quadratic, roots of 2 and minus 3, then we know the sum of the roots is minus 1, the product of roots is minus 6, thus the equation must be x minus the sum of the roots plus the product of the roots. Now where that's really useful is when we have those conjugate root types, because straight away sum of the roots, well, the surds are going to disappear. We have 4, product of the roots, difference of 2 squares, again the surds disappear, we get negative 1, and so our quadratic x squared minus the sum of the roots plus the product of the roots. So that's one place it's useful. Now sometimes we like to play around with these things, so they'll start off asking the basic ones usually. So what's the sum of the roots? Oh, minus b on a, 3 on 2. What's the product? Okay, c on a minus a half. But then we get to play around with them. So alpha squared plus beta squared. Now it's very tempting just to go alpha plus beta all squared, but of course that would not be true. It'll be alpha plus beta all squared, but minus twice the product. That's like a little formula if you like. So we just use that each time. All it really is our perfect square formula, and we've rearranged it. We've moved the 2 alpha beta to the other side. So in our question, it'll be 3 on 2 squared minus 2 times minus a half. Reciprocal, that's another common one. We can't just turn the two roots upside down. Treat it like an algebraic fraction. We get the sum of the roots over the product of the roots, and that one tidies up to be negative 3. One root is double the other. Now, if one root was double the other, instead of calling them alpha and beta, we'll call them alpha and 2 alpha. So the sum of the roots, in this case negative 6, and then the product of the roots, that'll be m, but now it's like I've got simultaneous equations, and so I can go and find m. Alpha will be negative 2, sub it into the other side, and eventually we get m equals 8. So a lot of playing around with the algebra. So quadratics, that's what we've just seen. The nice thing is with polynomials is it stays the same. So with a cubic, the sum of the roots is still minus b on a. But it's now you've got 3 roots, alpha, beta and gamma. The product of the roots is still c on a. But this time it's not product of the roots. It's probably better to say sum of the roots taken 2 at a time. So all the possible pairings. But we now have a new one, sum of the roots 3 at a time, or product of the roots minus d on a. A quartic, again that pattern would continue. Sum of the roots, there's now 4 possibilities, minus b on a. Taken 2 at a time, so there's now 6 possibilities, that would be c on a. 3 at a time would be minus d on a, but now if I take all 4 together, it'll be e on a. That pattern continues. If you've got any polynomial, assuming you make the leading coefficient a and work your way down, then the sum of the roots 1 at a time, so the shorthand way of writing that when you've got several roots is just sigma a alpha, is minus b on a. 2 at a time will always be c on a. 3 at a time will always be minus d on a. 4 at a time will always be e on a, and you could just keep going. 5 at a time would be minus f on a, 6 at a time g on a, and so on and so on and so on. Highly unlikely we'll get ones past a quartic, but I mean it would work. Now that idea about alpha squared plus beta squared, that pattern continues as well. So if you want to find the sum of the roots squared, that will always be the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. So if I've got a cubic, and for some insane reason we want to find 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma. Sum of the roots 1 at a time, 5 on 2. 2 at a time, minus 3 on 2. 3 at a time, minus a half. Now, In reality, I probably wouldn't find it 2 at a time, but I noticed this is part A, and I'm probably going to use it in other parts. So I'll find all 3 of the basics. So we end up, 27 on 2. Okay, reciprocals. Well, create the algebraic fraction. This time it's going to be 2 at a time over 3 at a time. Sub in those answers, and we get -3. This is what I was saying. Squares will still be sum of the roots 1 at a time squared, minus 2 times sum of the roots 2 at a time, and we get 37 on 4. Here's a very old question. They usually start off giving you some gift questions. So alpha plus beta plus gamma, a lot of people would make a mistake here. What answer do you think a lot of people are going to put? Yeah. But there is no x squared term, so it's actually 0. So alpha plus beta plus gamma is 0. Product to the roots, that one will be -1. Reciprocal, so it's all the standard sort of questions. So 1 on alpha plus 1 on beta plus 1 on gamma, and we get 3. 2003, so we know one root is the reciprocal of another. So 2 of the roots, 1's the reciprocal of the other. There'll be 3 roots in total, of course, because we're talking about a cubic. So in this case, instead of calling them alpha, beta and gamma, I'm going to call them alpha, 1 on alpha, and there'll be another root which we'll just call beta. So the product of the roots will allow me to find that 3rd root, the one that's not the reciprocal, because alpha times 1 on alpha, of course, will just be 1. So we know beta is -3. Now we want to find k. I'm not going to play around with sum and product of the roots from here, because we have another thing that's going to be a lot quicker. That's the factor theorem, because we now know -3 is a root. Therefore, polynomial -3 is equal to 0. So sub in, and we'll get k straight away. So that saves, playing around with some of the roots 2 at a time and creating simultaneous equations and all that. Okay. We have a cubic. R, S and T are all real numbers. The zeros are 1 alpha and minus alpha. Find the value of R. Well, this time we'll take advantage of the 1's alpha and 1's minus alpha. So if we do sum of the roots 1 at a time, now they'll cancel out. So sum of the roots 1 at a time leaves me with R being -1. They don't actually want us to find S and T, just what they would add together to give. Well, sum of the roots 2 at a time would give me S. So S is minus alpha squared. 3 at a time will give me minus T. T is alpha squared. They want S plus T. 0. Mind you, could we have done it another way? We now know R's -1, yeah? But we also know 1's a 0. So you could sub that in. So, well, hang on a sec. We know polynomial 1 is equal to 0. That gives us 1 plus R plus S plus T is 0. We just found R was -1. And so again, that gets us S plus T is equal to 0. A little bit quicker, anyway. All right.